Okay, then let's move to our next talk given by Davide about data structures for temporal queries on dynamic and temporal graphs.
Thank you so much for the introduction. Good afternoon, everyone, and welcome to this talk, which is based on a joint work with Luciano Gualà, Stefano Leucci, Guido Proietti, and Alessandro Strassiota. So in this talk, we will see how to design compact data structures, which are also known as oracles, that store some information about a temporal graph in our case, and are able to quickly answer to specific temporal path queries. And we will see two scenarios. The static one, in which the graph does not change over time, and the dynamic scenario in which the temporal graph is subject to specific updates, for example, insertion or deletion of edges or insertion or deletion of time labels. And the goal is to design oracles that can guarantee good trade-offs among the size, query time, and if the temporal graph is dynamic, also the update time. The temporal graph model we look at is very simple. So the temporal graph will be an undirected graph in which each edge has a set of integer time labels associated with it. And we look at the concept of no-strict temporal UV path. So you have already seen this definition, but let me repeat it again in such a way that we are on the same page. A no-strict temporal UV path is a path from U to V with a selection of a time label per edge of the path in such a way that when we traverse the path from U to V, the sequence of selected time labels is monotonically non-decreasing. Okay? So this is an example of a non-strict temporal path from U to V, which has a departure time of 1. It arrives at V within time, at time 6, and it has a duration of 5, which is the difference between the arrival time and the departure time. But somehow you don't have to worry about non-strict temporal UV paths because all the data structures we see can be adapted to work on strict temporal paths as well. The only thing is that the technical details will be presented for non-strict temporal paths. Okay? And these are the queries we want to support. In the temporal reachability query, we want to understand whether there exists a temporal path from U to V, which is restricted to live within the time interval that is given as input to the query algorithm. So here is an example of a query. So if I want to ask whether there is a temporal path from U to V, which is alive in the time interval 3, 7, then the answer to the query is true, and you see there a witness path. I want to support also earliest arrival queries in which I want to compute the minimum arrival time of a temporal UV path, which has a lower bound on the departure time from the vertex U. So we can depart from U no earlier than a time D, which is also given as input to the query parameter. And there is an example of an earliest arrival query. I want the earliest arrival path from U to V, which leaves U no earlier than time 3, and the answer is 6. Which is the arrival time at vertex V. Okay? In the latest departure, we have something similar. We want the maximum departure time of a temporal UV path that arrives at V within time A, whereas given as input to the query algorithm. And finally, in the mean duration, we want the mean duration temporal path that from U to V that is restricted to live in a time interval that is given as an input to the query algorithm. So for example, here the minimum duration path from U to V that is alive in the time window of 3, 7 is the path that you see highlighted there, which has a duration of 1. Okay? And before we move on, let me make some usable observations. As you can observe, temporal reachability queries are no more difficult than earliest arrival, latest departure, and the minimum duration queries, because if we want to answer, for example, to a temporal reachability query from U to V within a time interval dA, it's enough that I run an earliest arrival query from U to V with a departure time no earlier than D. And if the answer to this query is a value which is upper bounded by A, then the answer to the temporal reachability query is true, otherwise it is false. Okay, and something similar can be done for latest departure and minimum duration query. Okay, and furthermore, it is possible to observe, I think you all know this result, that earliest arrival queries are basically equivalent to latest departure queries. Because, for example, if I want to compute a latest departure from U to V in this path, with an arrival time that is 5, upper bounded by 5, and the answer is 3, then it's enough that I flip the sign of all the time labels, and I ask for an earliest arrival path from V to U, so the other way around, which departs from V at a time which is no earlier than -5. I get the answer -3, and this answer, if I flip the sign, is the answer to the latest departure query. So this means that the latest departure and earliest arrival queries are basically identical in some sense. Okay? And prior to our work, we were quite surprised because we found only a few papers published on the topic. And probably the most interesting one is the paper by Brito Albertini, Casten, Favencolo, where the authors designed an oracle for dynamic temporal directed graphs. But they were kind of maintaining a time version of the transitive closure of a directed graph. So this means that their data structure is pretty large because they are maintaining this kind of time the transitive closure in an explicit way. So the size of the data structure is n squared times tau, where n is the number of vertices of the graph and tau is the lifetime, which is equal to the number of distinct time labels that we can observe in the network. They can answer to temporal reachability queries in time that is logarithmic in the lifetime. They can support time label insertion solely in an amortized time that is upper bounded by n squared log tau. And the idea is very simple. Somehow, when we add an edge, when we add a time label, we can trigger the many events. So we have to update the transitive closure by adding many non-dominated fourth tuples to the solution. And interestingly enough, their results hold for uniform latencies, so we can add the latencies to the edges. So a time label is basically a pair, time at which the edge is available, and the latency, which is a non-negative value, modeling the fact that we require some time to traverse the edge. And in some subsequent papers, basically, same set of authors showed how to implement such an oracle if we want to store this oracle on a disk, and we want to minimize the memory accesses to the disk. Or in a more recent paper, they show how to design a compact version of such an oracle that is compact in practice, and they ran some experiments on it. And this is basically all we know about the problem on dynamic graphs because before we studied the problem. So, and here is the list of our contribution. We started to study this problem a couple of years ago. We haven't studied it quite intensively, so far we studied it only for forests, for trees, basically. And for static trees, we designed an oracle that supports minimum duration queries in a time that you see there. So we can choose an integer parameter t, and we can support the minimum duration queries in time that is order of t multiplied by some logarithmic factor. And the size of the oracle is capital M plus m squared divided by t squared, where capital M is the total number of time labels that appear in the graph. So it's basically the size of the tree, because we count the number of time labels, while capital L is the maximum number of labels we can have on a single edge. Okay, it seems that this trade-off is not very good, because if we consider the two extreme cases, for example, t equals 1, then we have an oracle which has a large size. Actually, the oracle is storing explicitly all the possible answers to all the possible queries, and we arrange the answers in such a way that we can retrieve them efficiently in logarithmic time. And if we consider the other extreme case in which we choose t to be equal to capital M, then we get an oracle which is very sparse, but it has a poor query time because it's at least linear in the size of the oracle. In fact, in this case, we do nothing. We just store a copy of the tree, and we run the most time-efficient algorithm that is known for computing a minimum duration query on demand. So it seems that such an oracle is not good, but the problem is that minimum duration queries are difficult queries we want to answer, even for static graphs, and in fact for static trees. And in fact, in our paper, we proved that the trade-offs that we provided are asymptotically tight up to polylogarithmic factors if we assume that the strong set disjoint test conjecture holds, as we will see in a short. Okay, so it's not possible to do better than what we did. Okay. So then we studied the problem for paths. So we assume that the topology of the path is fixed, but we can add and we can insert and delete time labels to the path, to the edges of the path. And we design an oracle that takes linear sides. It supports temporal reachability, earliest arrival, and latest departure queries in time that is order of log m. And it supports insertions and deletions of time labels in time that is order of log m. Okay, so as we can see, if we want to support temporal reachability, earliest arrival, and latest departure queries, we can do something which is pretty good. We obtain an oracle which has almost optimal sides, asymptotical optimal sides, and we can support the queries and the time label updates in a time that is logarithmic. Okay, and this is because basically earliest arrival queries and the latest departure queries satisfy structural properties like shortest paths in static graphs. So it's possible to compute earliest arrival temporal paths in such a way that any prefix of such a path is also an earliest arrival temporal path towards the end vertex of the prefix. And furthermore, in the same paper, we extended the problem. We extended the results to forests of rooted trees. So we obtain almost the same trade-offs. So for the earliest arrival and latest departure queries, we pay an additional factor of log L, but our data structure actually also supports the addition and deletions of new vertices and the additions and deletions of edges according to some rules that I'm going to present so far. So we cannot delete any edge in the forest of rooted trees, but we can delete all the edges of the form that you see on the left side of the slide. So we can delete an edge from V to its parent if the edge retains only a single time label. And when we delete the edge, V becomes automatically the root of the new formed tree. The edge additions we consider are basically the inverse operation. So we can add an edge from U to V with a single time label T, but V must be the root of a tree in the forest. So we obtain from the right side the left side. So the tree that is rooted at V is absorbed by the tree that contains the vertex U. Okay, so we cannot add and delete all the possible edges. So in general, we cannot add all the possible edges that we want, but one and the vertex of the edge that we add has to be incident to a root of a tree. Okay? And for the last result, basically, we can also add the latencies. And for uniform latencies, we can prove the same trade-offs that we see there for the model without latencies. And if the latencies are non-uniform, then we have the same trade-offs, but the update time bounds that we see there for all the three update operations become amortized. And the trade-offs hold only for the incremental and the decremental scenarios. In the incremental scenario, basically, we can add whatever we want. We can add time labels, we can add vertices, and we can add edges, but we cannot delete anything. In the decremental scenario, we can delete whatever we want, but we cannot add anything to the forest of rooted trees. Okay? And this is basically the main contribution that we provided so far. And in the rest of the talk, I'm going to present the results that you see highlighted here. So I will start with by showing that the bounds for static trees for minimum duration squared are asymptotically tight up to polylogarithmic factors if we assume that the strong set disjointness conjecture holds. So for doing this, let me define the set disjointness problem. So in this problem, we are given k subsets, S1, S of k, of a universe U, and we assume that capital N is the total sum of the sizes of the subset. And in this problem, we want to design an oracle that can answer to queries given I and j, are Si and Sj disjoint or not. Here is an example of a set disjointness problem instance, and there is the strong set disjointness conjecture by Goldstein, Levenstein, and Porat, which states that any oracle that can answer to a query in worst case time n requires a space that is n squared divided by t squared up to polylogarithmic factors. Okay? And we can use this conjecture to prove that the trade-offs of our oracle are tight up to polylogarithmic factors with a very simple reduction. So we build a temporal star, which has as many leaves as the number of sets of our set disjointness problem instance. Leaf vi corresponds to set S of I, and the time labels of the edge that is incident to vi is equal to the labels that are covered by the corresponding set. Okay, and now we can immediately observe that two sets intersect if and only if the minimum direction of a temporal path from the corresponding vertices between the two corresponding vertices with no time restriction is 0. Because if the two sets intersect, it means that there is an element in common, so I can traverse the two edges corresponding to the two vertices on the set using the time label of the element that they have in common. Okay? So this implies that in our case now, capital M, which is equal to the total number of labels we have in our temporal star, is equal to capital M. So by the strong set disjointness conjecture, we have that any oracle for static temporal tree supporting minimum direction queries in worst case time t requires that many space. And actually, it's possible to modify the reduction in such a way that it works even for trees with maximum degree 3. By losing a factor of log n on the sides of M. But this does not change the trade-offs too much. It changes the trade-off only by a logarithmic factor. Okay? Okay. So I showed you that the trade-offs of the static of the oracle for static trees supporting minimum direction queries are basically asymptotically tight up to polylogarithmic factors. Now, in the rest of the talk, I will present you the oracle for paths that supports time labels, insertions, and deletions. And then I will sketch how we can extend this oracle to work for the forest of rooted trees. So let's keep a path, temporal path, like the one that we see here. And the idea is that we want to build a data structure that models all useful left to right earliest arrival temporal paths. Because when we want to go from right to left, we can build the same data structure on the path that is mirrored somehow. Okay? And the idea here is very simple. We build an auxiliary forest of size m. So m is the total number of time labels we have in the path. And basically, the vertices are arranged in columns. We have a column per edge of the path. And the column contains exactly the time labels that are associated with the corresponding edge, which are modeled as vertices. And now, for each vertex, for each node, in column I, we define a parent of that node, which is basically its non-strict successor in the next column, if any. So, for example, here, for vertex 5, its non-strict successor is vertex 7 on the next column. For vertex 8, it is 8. For vertex 13, there is no strict successor in the next column. So this means that 13 has no parent, so 13 becomes the root of this auxiliary forest. Basically, what we are doing, we are modeling all earliest arrival temporal paths from left to right. Okay? And in fact, if we want to answer to an earliest arrival query, so we want to know what is the earliest arrival time at V4 if we can depart from V1 at a time that is no earlier than 5, we just look at the column of the first edge that we have to traverse, which is edge 1. We compute the non-strict successor of 5, which is 7. And then we move 2 steps forward along the tree. And so we get 15. Basically, 15 corresponds to the second ancestor of 7. And 15 is the right answer for the query. Okay? The problem with this approach, so it works perfectly for static trees, because we can model this auxiliary forest in a top tree, so we can answer to an earliest arrival query in time that is logarithmic. But the problem is that this data structure cannot be made dynamic in the way it is now. Because if we add a label, for example, we add the label 10 to the edge E2, there is the problem that we have to update too many pointers if we want to rebuild this tree. that is modeling all the list arrival left to right temporal paths. And so the problem is basically that there might be internal vertices of the forest of trees that have a large degree. Okay? And to fix this problem, we want to reduce the degree of the nodes to a constant. And we do this with a very simple rule. So for each node, let's take in this example node 7, there are two candidate nodes that can be parents of 7. One candidate node is the non-strict successor in the next column of 7, like we defined it before. So it is 12 again in this example. But then, and that's the blue candidate parent, and then there is also the red candidate parent, which is the strict successor in the same column of the node we are considering. So for 7, the strict successor basically in its column is 8. And now, among the two parents, we choose the one with the minimum time label, which is 8. And in case of a tie, the red parent wins. So in this case, the parent of 7 becomes 8, and we connect 7 to 8 by a red edge to distinguish that 8 is a red parent. And this is the way in which we rearrange the entire data structure. And what we can show is that every internal node of the data structure can have at most 2 children in this way. So we already fixed the problem of updating the data structure, because when we add a new time label, we all have to update a constant number of pointers. But somehow we created a problem for the earliest arrival queries. And now we have to fix the problem for the earliest arrival queries. To fix the problem for earliest arrival queries, we use weights on the edges. So each blue edge has a weight of 1, because a blue edge is modeling the fact that we are going to traverse the edge. And each red edge has a weight of 0, because a red edge is modeling the fact that we are waiting at a vertex. We are not moving forward from left to right along the path. And now, if we want to answer to an earliest arrival query, again, in this example, we want to know what is the earliest arrival time at V4 if we can depart at V2 at a time which is no earlier than 5. Then we find the non-strict successor of 5 in the first edge that we have to traverse, which is the column corresponding to E1. So the non-strict successor of 5 is again 7. And then we compute the ancestor that is at a weighted distance of 2, which is again 15 in this case. In case there are multiple ancestors which are at the same weighted distance, we have to select the deepest one, which corresponds to the vertex that contains the right answer to our query. And this is the way in which we build the oracle. So each column is arranged in a dictionary. So we can insert and delete new vertices in each column in time that is log of L, where L is an upper bound on the number of vertices we have in each column. The total size for building all the dictionaries is order of M, because capital M is the total number of labels that we have. The building time is also pretty fast, and we can answer to successor queries in time that is log of L, the height of the column, again. And the auxiliary forest is stored inside the top tree. So the size of the auxiliary forest, the size of the top tree is linear to the size of the forest. So it's order of M. The building time is linear, and we can do all the operations we need to do in the top tree in time log of M. So this is the way in which we build the data structure. Okay, and now let me quickly sketch what we do for the forests of rooted trees. Basically, we use the same idea for paths. And the idea is that if we have a tree that is rooted at X in our forest, like the tree that you see here, we want to model all useful upwards earliest arrival temporal paths. Okay, and we recycle the ideas that we saw for paths. But if we recycle the same idea in the way we applied it for paths, we run into the same problem that we had for paths, is that we can create many vertices in the auxiliary forest that have large degree. And to reduce the degree of a vertex, we have somehow to group the vertices according to some rules that I don't have the time to define right now. But if we do this in a clever way, basically we can reduce, again, the number of children of each internal node of the auxiliary forest to 2 in such a way that when we have to add a new time label, we only have to update a constant number of pointers. And then to fix, and then to implement the earliest arrival query, somehow, in the case in which U and V are two vertices which are related, so they are in two different branches of the tree, we have to compute the least common ancestor of U and V, which is X, and we have to break the earliest arrival query from U to V into two earliest arrival queries. One from U to the list of common ancestor, which is an upward earliest arrival query that can be still answered in time, which is log of M, because it's exactly the same idea that we used for paths. And once that we know the arrival time at vertex X, which is modeled by dx in the pseudocode of the algorithm that you see, we run an earliest arrival query from X to V with the departure time from X, which is lower bounded by d of X. But since the query from X to V is a downward earliest arrival queries, we don't know how to make this query in a time that is logarithmic in M. So we have to kind of doing a binary search, and we have to pay an additional factor of log L to make the downward earliest arrival queries. But somehow the details can be found in the paper. And this implies that we have somehow for forest of root F3 similar trade-offs, except for the earliest arrival related departure queries, for which we have to pay an additional factor of logarithm of L. So to conclude, prior to our work, results were known only for directed graphs that supports temporal reachability queries and time label insertions. And we designed oracles with good trade-offs for static trees that support minimum duration queries, for which we provided asymptotic time tight bounds up to polylogarithmic factors, even for trees of maximum degree of 3. For dynamic temporal forests or rooted trees, we designed an oracle that supports temporal reachability, earliest arrival, and latest departure queries, and all the types of updates that I mentioned. And I mentioned that we can extend these trade-offs if we add the latencies, but only in the incremental and decremental scenarios. And so, as you can see, there is a lot of work to do for the problem of designing data structures that maintain information about temporal paths in both static and dynamic temporal graphs. And probably the problem that is of interest is whether it is possible to design oracles for fully dynamic temporal forests that support latencies with latencies that supports temporal reachability, earliest arrival, and latest departure queries, and try to get the same trade-offs we obtained for the same scenario, but only for the incremental and the decremental cases. If you find this problem a little bit difficult, you can try for a problem that appears simple, but it is not that simple. So consider a path that is static, and we want to design an oracle that supports minimum directions queries. And the question is whether it is possible to obtain better trade-offs than the one we proved for trees. Because for static paths, we don't know whether the bounds we provided are tight or not. Another problem is to design oracles for dynamic trees that support the minimum direction queries and time label updates only, because it seems that the approach we used for static trees can be somehow extended to make the tree dynamic and support time label updates, but we don't know how to do this. In general, you might want to design oracles for temporal graphs, and if this problem might be difficult for you, you might want to consider some useful restrictions, like, for example, considering simple temporal graphs or graphs of bounded tree width, for which probably the approach that we used for the dynamic temporal forest can be extended. We don't know, we haven't explored this scenario. And finally, you might want to support other types of queries, So if we consider the model in which we add latencies, there are other queries that we can support, like, for example, the minimum travel time or the minimum waiting time. But be aware that these two queries are at least as difficult as the minimum duration queries. And we can prove similar conditional lower bounds that we showed for minimum duration queries, use again the strong set intersection conjecture. Okay, this is all I wanted to talk about. Thanks a lot for your attention.
Thank you very much. Are there any questions?
So you did all of this for the non-strict case. I was wondering if you restricted yourself to strict paths, do you think that would make anything easier?
No.
No. So you don't think the non-strict...
For the problems that we consider, the two notions of paths are equally difficult, I would say.